The first vehicle ever driven on another world looked strange. It had no rubber tires. It had just 1 horsepower. It folded up like a camping chair. And somehow, this bizarre little machine became one of NASA's greatest engineering achievements. Every strange feature solved a problem no one had ever faced before. So, what were they thinking? Here's the detail that still catches people off guard. Work on this vehicle started before the first moon landing ever happened. Engineers were sketching out a lunar car in the early 1960s, years before Neil Armstrong took a single step. Which means they didn't have Apollo 11's data, didn't have Apollo 12's data. Nobody on Earth actually knew what the lunar surface felt like beneath a person's feet. How hard was the ground? How much dust covered it? Would a wheel sink the moment it touched down? Nobody could answer those questions with real data. So NASA's engineers had to do something almost impossible. Design a 4-wheeled vehicle for terrain nobody had ever physically explored. They tested prototypes in laboratories, dropped them from aircraft flying parabolic arcs to simulate low gravity for a few seconds, dragged them across artificial craters in the Arizona desert. But at the end of the day, they were still guessing. If they guessed wrong, astronauts could end up with a vehicle that simply couldn't drive on the moon. Everything about this machine was an engineering gamble, and once you know that, its strange design choices suddenly make perfect sense. NASA had one immediate problem. How do you fit an entire car inside a spacecraft that barely had room for 2 astronauts and their equipment? You don't. At least, not unless the car folds. The lunar roving vehicle traveled to the moon, folded on the side of the lunar module in an open compartment. Once on the surface, 2 astronauts wearing bulky pressure suits had to deploy it by hand. Fortunately, most of the process happened automatically. Torsion bars snapped the wheels into position. Pulleys lowered the frame onto the surface. But mostly automatic still meant 2 astronauts, wearing some of the most restrictive gloves ever designed, had to finish the deployment on the first attempt, with no backup vehicle waiting nearby. The folding mechanism wasn't a clever extra feature. It was the only reason the rover could go to the moon at all. Now here's a question. If you had to build a vehicle for the moon, would you use rubber tires? Most people probably would. NASA said absolutely not. Instead, the wheels were built from zinc-coated steel wire mesh with titanium chevrons for grip. No air, nothing to puncture, nothing to go flat. So why abandon something as proven as rubber? Because the moon changes the rules. Rubber doesn't cope well with the moon's extreme temperature swings, from around minus 208 degrees Fahrenheit to over 250 degrees Fahrenheit. And then there's the vacuum. Materials behave differently when there's no atmosphere at all. So engineers designed wheels that flexed instead of breaking. They paired them with a lightweight suspension based on torsion bars, while the flexible wire mesh absorbed much of the rough terrain. At first glance, it almost looks under-engineered, until you remember one thing. The moon's gravity is only 1/6 of Earth's. Every bump, every rock, every crater edge pushes back with only a fraction of the force it would here on Earth. The moon itself quietly helped the suspension do its job. This may be the strangest number on the entire vehicle. The lunar rover had less power than many riding lawnmowers. Each wheel had its own electric motor. Each motor produced just 1/4 of a horsepower. Together, 1 horsepower. That's it. Yet this tiny machine carried 2 astronauts, their scientific equipment, and hundreds of pounds of lunar samples. How? Once again, the moon changes the rules. 1/6 gravity dramatically reduced the effective weight. There was no air resistance, and the rover only needed to reach around 8 miles per hour, although Eugene Cernan briefly pushed it to about 11.2 miles per hour during Apollo 17. The rover itself weighed about 463 pounds, yet it could carry more than twice its own weight. On Earth, that sounds almost impossible. On the moon, it worked beautifully. Now imagine this. You're several miles from the lunar module. Your oxygen supply is slowly ticking down. And suddenly, one of the rover's motors fails. NASA expected that possibility. In fact, they had a rule. Astronauts were never allowed to drive farther than they could safely walk back if the rover completely stopped working. This was known as the walk-back limit. Even so, the rover itself had another layer of protection. Each wheel motor could be manually disconnected in the field. A seized motor didn't have to disable the entire vehicle. It's a tiny engineering detail, but out there, it could mean the difference between driving home or walking home. The lunar rover wasn't just transportation. It was also a television studio. Mounted on the front sat a high-gain dish antenna and a television camera. But here's the remarkable part. The astronauts weren't operating it. Controllers back on Earth were. Take a second to think about that. In the early 1970s, someone sitting in Houston could remotely pan, tilt, and zoom a television camera, sitting on another world. The antenna continuously transmitted live images back to Earth, while the astronauts explored the lunar surface. It was one of the earliest demonstrations of remote robotic operation across nearly 250,000 miles. Only 4 lunar rovers were ever built. 3 flew to the moon. 1 remained on Earth after later Apollo missions were canceled, but together, the 3 rovers drove a combined total of about 56 miles across the lunar surface. That's roughly 90 kilometers. The entire program cost around $38 million, roughly $280 million today. And every single one of those 3 vehicles is still sitting on the moon today, exactly where the astronauts parked them. Which brings us to one final question. All 3 lunar rovers are still sitting on the moon. But if Artemis astronauts walked up to one tomorrow and installed a fresh set of batteries, could it actually drive again? Here's what works against it. The original silver zinc batteries were designed for a single mission, not 50 years. Their lubricants have spent decades exposed to hard vacuum. Lunar dust slowly grinds away at moving parts, and every component has endured 50 years of cycling between roughly minus 200 degrees Fahrenheit and 250 degrees Fahrenheit, while being exposed to constant radiation. Metal fatigues. Wiring becomes brittle. The once flexible wire mesh may no longer flex at all. So, would fresh batteries really be enough? Would the motors still turn? Would the steering still respond? Would the wheels survive the very first bump? Nobody truly knows. Not until someone actually tries. And maybe that's one of the most fascinating things about the first vehicle ever driven on another world. It isn't just a museum piece. It's still waiting, exactly where we left it. So here's my question for you. If Artemis astronauts found one tomorrow and had a brand new battery pack, would you trust it to drive? What part do you think would fail first? Let me know in the comments. The lunar rover looked strange because it wasn't designed for Earth. It was designed for a world where almost every engineering rule had changed. And more than 50 years later, it's still one of the most extraordinary vehicles humans have ever built.